happy to introduce our next speaker, Sigal Oren, and Sigal will talk about revenue maximization with minimal information. Thank you, Sigal.
Thanks, Michal, both for the introduction and for inviting me. This is a really nice day. So I'm going to talk today about revenue maximization with minimal information. This is a joint work with Yael Shlagi, Shahar Dovzhinsky, and Jacob Leshner. And to get us started, let's first look at two examples. So in this example, we think about this guy. He's a seller, and he needs to sell these satellites. Now, initially, what he knows is that there are two bidders, two dish network companies, and their values are uniformly distributed in the support between 100 million and 400 million. Now, our seller asks himself, what kind of information about the bidders can be helpful in order for him to design the auction in a way that he will collect more revenue? Now, one piece of information, of market research that you can do or ask someone to do is to look into the infrastructure of these two companies. And what he might find out is that this specific satellite is more compatible with the infrastructure of the dish network. So he concludes that the dish network has a higher value for this satellite. Now, once he learned this information, he could design an auction that takes this into account in order to get more revenue. Here's another example. So now a seller is selling lumber. And let's say he needs to sell this lumber in a specific town. And in this specific town, there are two construction companies. Again, initially, what he knows is that their value is uniformly distributed. Now the support is between 20K and 40K. And what he now asks himself is, what kind of information about the market could help him collect more revenue? And one thing you might notice is when he comes to this town, say by train, that there's a lot of cement in the train station. So that might hint him that there's a very big construction project going on. And if there is a big construction project, there's also need for lumber. So he concludes that in this market, at least one of the players is big, has a high value, higher than 35K. And again, once he has this information, he can use it to design a specific auction and collect more revenue.
So you're moving, so here we're not just marginals, now we have something over the joint. Is that the point that you are making? Because when you said X and Y, you didn't say anything about the correlation till then. So
let me go to the next slide to be clearer.
Okay.
Let's wait for you just a second. Okay? Okay, so this is the general framework that we are thinking about, and I'll give you more details in a few slides. So we have a seller, and the seller initially knows the distributions that the bidder values are sampled from. And for this talk, think about just uniform distribution with support between 0 and 1. We are going to look at these kind of pictures. We'll have two bidders, the X bidder with a value between 0 and 1, and the Y bidder also between 0 and 1. So this is the valuation space. Independent, yes. And our seller can get more information on the realized values of the bidders by asking a single yes-no question. So he can get one bit of information. Any question he would like to ask, he can ask. So what it means pictorially is that our seller can partition the valuation space into two parts. So in the seller example, we partition it into X greater than Y and Y greater than X. Yeah, so this is a general framework. Now, the seller, condition on the answer, can run a revenue maximizing auction on the induced distribution. Typically, once we ask the question, the distribution is going to be correlated. So we are no longer in the independent value space. And the high-level question that we ask here is if we can magically get a correct answer on any question we would like, just single bit, just one yes-no question. Which question would we like to ask when we want to maximize the revenue? Yeah, so this is the high-level question. This kind of question work is related to the literature on information design. So usually in mechanism design, we think about information as exogenous. In a typical information design setting, we have bidders that are uninformed, so they might don't know the true value, their value. The seller has more information, and he is going to release information in order to influence the strategic behavior of the bidders. So, for example, you can think about a seller that can decide the accuracy by which the bidders would know their value and use it in order to get more revenue. Our setting, which we think about as informed design, the less informed party is the seller. And our seller is going to collect more information, and we will focus on a limited amount of information, in order to determine which mechanism to run, which mechanism will get him more revenue. A useful way for thinking about this additional information is a distinction by Bergman and Morris. And they distinguish between two types. So first we have literal information design. And in literal information design, we actually think about specific settings, like the satellite example or the lambda. And how might a seller specifically get more information in this setting? And whether he wants to keep exerting effort to find his buyer to get more information. On the other hand, what we're going to focus on is metaphorical information design. In a metaphorical information design, we don't restrict ourselves to specific questions or specific data might be attainable, but we can ask any question we would like. We have this magic goldfish that anything we ask, we get a correct answer. And we want to know which question to ask, kind of quantify what is the value of this one bit of information. How much can we gain from it? Let me
Just a question.
Yes.
Who is going to give the answer? I mean, each buyer knows his own valuation. He may not know the valuation of the other. So what's the device by which this information, that X is less than or equal to Y, is revealed? Who is?
In a metaphorical approach to take, yes, the fish is going to get an answer. But what you're asking is a literal kind of question. And for this was the examples in the beginning. So in the beginning, we got the information X greater than Y. We concluded it from the compatibility of the satellite to the specific infrastructure. So it's something that we concluded by doing some market research. Okay, so
Also, the realized values to know, it's not so easy. I mean, okay.
I understand. I agree it's not easy, but there are kind of.
Because again, you want to get a reliable answer, a correct answer from, and really this information is distributed. It's not centralized. So that's what I'm saying. There is a question here.
I agree, and I agree that when you take the literal approach, you should be much more specific about how you attain this information. But as a first step, we're thinking, okay, say you can do anything, how much can you gain? Is it even worthwhile to start thinking about this kind of stuff?
Not all bits of information are the same. Some bits are easier than others.
Yes.
Say one bit is the same.
Yes. For the purpose of this talk, all bits are the same, but yes, you are correct. It's a partition, yes. I'm going to briefly go over the related literature. So as I mentioned, it's related to literature on information design. Bergman and Fassbender was this work about independent private values, that the bidders don't know the values. The seller decides on the accuracy by which they know the values. And kind of the high-level idea is that the seller doesn't want to release all information, wants to release some information in order to maximize the revenue. This is also related to the literature on health leads. It's kind of a different approach. They are thinking about non-strategic work that focus on the computational efficiency. So if you get one bit of information, can you construct an algorithm that will be much more computationally efficient? Okay. So here is a more formal version of our model. We're going to have a single indivisible item, and we must allocate this item. We'll have two bidders, X and Y. This will be the value of bidder X, this is the value of bidder Y. Both values are joined independently, form a distribution F with supported 0, 1. For the talk, just think about the uniform distribution. Okay. And now a seller is going to choose a partition into two parts, Q and Q bar. The partition induces two correlated distributions, FQ and FQ bar, and then an instance is realized. If XY is in Q, the seller runs a revenue maximizing auction for FQ, and if XY is in Q bar, he would run the revenue maximizing auction for FQ bar. Now, since we assume here that the seller is the less informed party, we are going to focus on mechanisms that are ex-post instead of compatible. Because the bidders might know more. Okay, first of all, the bidders do know the valuation, so it's a private value model, but the seller doesn't know how much the bidders know about the distributions of the other players. Okay, they might have some information, but the seller doesn't know. And for this reason, we focus on mechanisms that are exposed and self-compatible and also exposed individually rational. So this is the playing field. Any questions so far? Okay, good. So we're going to ask this question of which partition is the best, and we will focus on three natural families of partitions. The first one we call increasing partitions, and they are characterized by this increasing line that split the square into two parts. They correspond to comparison questions, like we've seen in the satellite example. Is the value of beta x greater than y, or is the value of beta x is greater than some function of the value of beta y? Now, what is increasing queries do is break the symmetry between the players. So initially, since we assume that the values of both bidders are drawn independently from the same distribution, they are completely symmetric. But once we ask this question, then the symmetry is break. And we try to understand how much you can gain in terms of revenue by breaking the symmetry.
So when you say increasing, you also mean concave or?
No, just increasing.
So it's not necessarily comparison questions, if I understand.
It's doing concave for one, if you look here, it's convex for the other. Just change x and y.
No, but
So-
can it be like an S shape?
I mean, as long
Yeah.
as
This
it's
point, is this point?
interesting, yes.
Let's hear the
Okay.
comments. And
The second type we think about are decreasing partitions. So they are characterized by this decreasing line. And they correspond to questions like the Lamar example. So it could be something about the maximal value of a player in this setting. So you get this square. It can also be something about the average value of bidders in the market. Right? So does x plus y greater than 1? Actually, that's the decreasing line.
Sorry, why does that represent maximal? Like what?
So this would be the space in which the value of there is at least one bidder, that its value is greater than, let's say, this point is half. It will be half. Okay. So this partition is whether there's a maximal bidder with value less greater than half or less than half. These are the two ones. The last type of partitions we think about, we call them symmetric partitions. So they are symmetric with respect to the y equals x line. And what we ask here is about the competitiveness of the market. Is this a competitive market where the values of the bidders are pretty similar? Intuitively, if this is the case, then we can just run a second price auction and we're not going to lose too much. So is this a competitive market, or is this an unbalanced market in which we have one bidder that has significantly higher value, and then we need to do something different? So the plan is that for each type, we are going to find out which is the optimal partition, and then we're going to compare between those three types. So we'll start by characterizing the auto partition for the symmetric and increasing partitions. Then we'll talk about decreasing partition, increasing partitions, and finally, what we are going to see is that from all of these partitions, the one that is best is the symmetric, the optimal partition for the symmetric increasing. So talk about this. Okay. So what we're thinking now is about symmetric increasing partitions. The definition of symmetric here is that xy belongs to Q if yx belongs to Q. And by increasing function, what we mean is that we have this function t, and for y greater than x, like Q, then xy is in Q if y is less than tx. So this is how we characterize this partition. The economic interpretation here is we ask whether this is a competitive market or not. Competitive, we are in the purple part, not competitive in the blue part. One thing that's worth mentioning is that under this class of symmetric inclusive partitions, we also have this partition, which is both decreasing and symmetric increasing if we set t to be this line. So we also have these kind of partitions. It's going to be some something useful to note later on. Okay. And the question we ask is, what is the best symmetric adjacent partition? So here's our theorem. If F is a regular distribution, then the symmetric partition defined by T, which equals the inverse of the virtual value of X, is optimal. And furthermore, the allocation that we are going to implement is the efficient allocation. So we are always going to sell the item to the bidder with the highest value. If we look at the uniform distribution, then the virtual value,
Optimal among all possible partitions or only the ones you consider?
only the ones we consider. This is optimality for the next few slides will be in each class for this class. Yeah, so this is optimal for optimal symmetric adjacent partitions.
Okay.
Okay, so for the uniform distribution, the virtual value of X is 2x minus 1, so the inverse is half plus x over 2. And if you do the math, you see that this partition collects a revenue of half. Now, this is in contrast to if we don't have any information, then since we are required to allocate the item, the best thing we can do is run a second price auction and get a expected revenue of 1/3. So that's a significant boost to the revenue of the mechanism.
How much you collect from the symmetric part, from the competitive part, so from the close to diagonal, and how much from the outside, just to get your, I mean, this 1/2 is an average of two numbers, yes.
Yes.
And do you know what they are? Just
I don't remember. Like I have it in, we have it in the
I
paper.
mean,
but,
is there some equalizing that you are taking the regions so that, because there is clearly
It's
more
not the same.
competition in the middle, and so maybe it's easier to collect on the outside than in the middle. The question whether the line gives some equalizing of those two. I don't know. Just, I have no clue.
no, you collect different amounts of revenue in the two
Okay.
in the two parts. I think we collect more from the blue part, but
It's easier. It's easier to collect from the blue part.
yes, exactly. Yeah, I mean, from all of this, you don't collect that much. Yeah. Okay. Any other questions?
A big one. There is one with a big valuation there.
Okay. So let me give you some intuition for the proof. So first of all, what we shall indeed we can expect that for the parallel part, the optimal auction is just a second price auction. So this is what we do here. And we shall also show that there exists an optimal partition such that when we're in this part, so in this part, yes,
You said that you must sell the item.
yes,
Okay, without reserve. Okay, just second price.
yes, this
Okay,
is
okay.
just second price. Yes. Okay, so here we just on second price. And here when we are above the TX line, then we sell to the white player at the price of TX. So this is, and similarly here, we sell to the X player at this spot. So this is kind of doing, in the middle we do the second price, and outside we do this fancy reserve price that depends on the other bidder. And the information allows us to do that.
What is the mechanism?
We have two mechanisms.
Yeah,
So
second price option.
second price auction and just reserve price. The reserve price is defined by the boundary here and the boundary here. So here, if we have an instance xy, which is in this part, we sell to y at price tx. So this is the mechanism of the blue part.
And Avora you sell to X.
Here we say, exactly, we sell to x at t minus 1y. Yes,
Going back to my previous question,
Yeah.
is the condition that you must sell the item binding? What if you don't impose that restriction?
then the analysis is going to be slightly more complicated, but we think that everything else would be pretty much the same. It's just easier to analyze things like this. When, all the partitions would look slightly different,
The reserve price is a function of the value, player's value? Is that something, is that a valid mechanism?
Okay, remember that we have information. And the information allows us to essentially give a reserve price that depends on the other bidders. The information allows us to know whether we're in the purple part or in the blue part.
Yes.
And once we have this information, then we know that we are here, we know the value of Tx because we define it,
Yes.
so it's fine to sell to bidder Y at the price Tx.
We don't know X.
But what if you see X, this determines the price? So how do you know that the value of Y?
No, you see X and Y and you check if Y is a larger than Tx.
So,
Okay, you see X and Y, you see that Y is larger than X.
Than
and
Tx.
You don't see that Y is larger than X. It's
No.
like if you set a supposed price for Y
It's a direct
at
mechanism.
price
Seems like a direct
Tx
mechanism.
and price for X at price T minus 1 X. So you just set two prices for the players and only one of them agrees.
No, but you need to know X and Y to set this price.
Mhm.
You need to know X and Y to set these prices.
You just ask.
you said
every player
each player
gets
that
a
price
price.
with the other.
Yeah, so it's not like, okay, the way to discuss now, you give two prices, one for X, one for
Yeah,
Y.
yeah,
and
you can,
only one of them.
yeah, it's better to
accept
think
it.
about it like that.
It's not that you know which price to give. It's there are two prices and
Yes.
whichever works out.
Yeah.
But you ask for X and Y.
Yeah.
Yeah, you ask for X and Y. The price of Y depends on X and the price of X depends on Y, and it works out because only one of them is going to accept. Any other questions? Okay, so how we should choose Tx in order to maximize the revenue? So we need to solve the following optimization problem. So if this is X and Tx, then we know that with this probability, so Y minus ftx, we're going to sell to Y and get Tx. And with probability ftx minus fx, we will sell to X, and we will sell to Y and get a revenue of X. When we take a derivative compared to 0, what we get is that we should set Tx to be the inverse of the virtual value of X. Again, the inclusion here is that for every X, we do the optimal algebraic limit offer with a fallback of X. So if the value of Y is less than this taken limit price, we can still sell it at X. And as you can see, the allocation we implement here is the efficient allocation. And when the value of Y is greater, we sell to Y. The value of X is greater than the value of Y, we sell to X. Any questions?
So again, T is what is the posted price. So what is
T-
T is the line. T is the separating line.
T plays two roles. So first it plays the role of defining the partition, and then in the blue partition, it is the posted price for Y and X. Okay, so it plays the double role.
So at the end, it's a posted price mechanism. The only question is what
The
price.
blue one, at the blue part, specifically here at the blue part. The purple part is second price auction.
Second price.
Any more questions?
But why they're not cheating actually?
They can cheat because they're not. We are assuming that we have this goldfish that gives us the correct answer on whether the instances are here and there.
No, but the value of X and Y.
It's the dominant strategy. They don't have a reason to cheat. The dominant strategy mechanism. Any other questions? Question?
Well, just other metrics. You said X post IC, you mean dominant strategy?
Yeah.
There is no issue beyond that, right? It's just dominant.
Dominant strategies.
Dominant strategy overall or only for each part?
Each part separately.
Each part separately is dominant strategy, and if you look at the whole, then it's exposed or it's difficult to even formalize.
If you
Partition
look
was
at
given.
probably not even
They were not the ones who gave the partition.
Yeah, they
Partition
don't-
was given by the goldfish.
Yeah, it's common knowledge to, everybody knows. The bidders know whether.
They know, but it's
Because in fact they assume they know both valuations, right?
I don't
They
assume
don't.
anything about what they know.
But they know at least, they know if they are impure or not impure.
Yeah, they can know that. I mean, we have dominant
The
dominant
seller
strategy
knows
mechanisms.
directly. The
sellers knows
Sellers
whether
knows
it's
that
Q
it
or
is a
not
mechanism.
Q.
Yes,
It's
so,
a mechanism.
Independent of.
so another way
From
of
the mechanism they put, they can use it there in Q or not.
another way of
Doesn't matter.
So
another
you're
way
not, so in other words, you are not requiring that the mechanism as a whole would be DC.
I can't require that, and if they require that, I wouldn't get anything better than
The optimal DC.
DSIC. Yes. Another way to think about it is that the seller can choose choose two dominant strategy mechanisms, and this fish is going to tell him which one to use, which one is better to use. Okay, so this is another way of thinking about what we are doing here. Okay. Any other questions?
So you choose these two dominant strategy, these two mechanisms, and
Yes.
this is testing what which is optimal
Yeah.
to run in the
In the
given
specific.
situation.
Now, which of them should I run?
So yes, the maximum of the revenue of the two mechanisms.
No, yeah.
The average because of
Probability of Q
the
times what you get from Q plus probability of 1
Yeah.
over Q.
Yeah.
That's the revenue you get from that.
One question?
Yeah.
About the function t of x, we said earlier that we don't assume it's concave.
Yeah.
But then if you go back to the drawing in the previous slide, can't the two t of x's and the t inverse collide? Right, the drawing is a little bit simplifying, right? Because it might be like an S curve and this one's an S curve and then they collide in the middle. And have like some overlap, negative overlap.
So you could define probably that the purple part would be till the intersection and the blue part would be outside. But I think so. The definition that we have here, like this, would say exactly something like this. So till the intersection it would be the purple part, and outside it would be the blue part, and essentially you would ignore this. Like, yeah. Okay. Next up, we are thinking about optimal decreasing partitions. Now we have a decreasing function that separates the square into two parts. Xy belongs to Q if y is less than px, this is the function. And as we said now, the interpretation here is that we have some information about the market. So this would be, for example, whether the value of x plus y is less than 1 or greater than 1. Something about the market. And again, we ask, what is the revenue maximizing decreasing partition? So one simple thing we can think about is just take Meyerson optimal auction with reserve and ask our goldfish whether this auction was able to sell the item or not. If it sold the item, fine. If not, we are going to sell the item by a second price auction. So this is a well-defined two auctions, well-defined conditions, and it's going to look like this. Yeah, below the reserve price we just do second price. Above the reserve price we run Meyerson optimal auction. So here we start with the reserve half, here with the reserve half, and here we do the second price auction. And the revenue that we are going to collect from this is 5 over 12, which is the revenue from Meyerson optimal auction through the distribution. And with probability quarter, we will be in the purple part and collect a revenue of 1 over 6. So the total revenue that we collected is 11 over 24. But in fact, we can do something better, right? So in Meyerson optimal auction, this reserve was computed and take into account that if we don't sell the item, both values are below the reserve, then we get a revenue of 0. But in our case, we do get some revenue, so we should increase this reserve price. And the optimal auction, to do this is to set the reserve price to 2/3 instead of 1/2. And this way, we collect a revenue of 13 over 27. And in fact, this is the optimal decreasing partition for the uniform distribution. This is exactly how it looks like. Okay, this is the theorem we prove. We prove that if F is a regular distribution, then there exist two constants, such that the partition we ask is whether X is below this reserve price for X, and Y is below this reserve price of Y, and this is optimal. So pictorially, we have this rectangle for the purple part, and the blue part is the less.
It can be non-symmetric, despite the fact that they were IID, right? The marginals were
They
the
were
same.
IID.
So, no, it could be. I mean, I'm not saying it can't be, but I'm asking.
It's a good point. This is what we know how to prove. We suspect that the optimal thing is Rx equal R1. But currently,
So basically, you have two solutions, one like this and one like that. If they are different, you can also interchange them.
yeah,
The problem is symmetric to start with.
the problem is symmetric,
But you're saying
and
the optimal solution may be non-symmetric.
we don't know how to prove that the optimal
No,
solution is symmetric. Like, we think it is symmetric, and intuitively it's supposed to be, we think it's supposed to be symmetric, but this is what we currently know how to prove. Yeah.
So you tried some, beyond uniform, you tried several others and it all came out symmetric?
Whichever distribution we tried, yeah. So for the distribution, we have both Ry and Rx equals to sum. This is the revenue we get. I want to show you a bit why this is a challenging proof. For this, I want to first take a detour and tell you what we do know about cohort distributions. And it's not that much. So for quality distributions, we can define conditional virtual values that are pretty similar to virtual values, only now we use the conditional distribution. So we have here the quality distribution FQ, the CDF will be FQ like this, and this is a small q, and the conditional value, we look at the conditional value of VI given Vj, and these are just what you would expect to get. And the analogous definition to implicit virtual relations is requiring that FQ is single crossing. So a distribution FQ is single crossing with respect to the conditional virtual values if first for any VI greater than V prime I and Vj, we have the conditional virtual value is increasing in VI. So this is exactly the same condition as regular virtual values. And second, we have this on the value we condition on, that if VI is greater than V prime I, then the conditional value of Vj cannot increase. And if we have this,
So the first one is regularity, right?
it's essentially regularity.
Conditional regularity, let's
Yes,
say.
yes.
And the other one, you are changing the condition.
We are changing the condition. Yes.
Okay, so that's a different kind of thing.
Yeah, this is an actor.
There's no counterpart in the independent case.
No. This is like in the independent case, this is like regularity, and this is something you need to add for the conditional case.
And what's the intuition for that? Is there any, where does it come from?
It's
second
also
one, I mean.
it's also kind of monotonicity, right? So if the other beta has a higher value, it doesn't make sense that suddenly your conditional value would increase, right? So that's kind of the intuition. Or if it does increase, okay, why do we define single crossing? What's good about the single crossing is that when the cohort distribution has this property, single crossing, then essentially everything we know from the independent case holds. So essentially,
Single crossing is really, sorry, so single crossing is really the second condition. The first one is regularity and the second one is a single crossing.
it's both.
Okay.
It's both because the conditional values, right? I mean, but yes, this would mean that the conditional virtual value is regular. I mean, increasing. Yeah. And again, when this holds, we know exactly how the optimal option looks like. We are just going to sell to the bidder that has the largest the conditional virtual value. So everything behaves as expected. But if the distribution is not single crossing, then we don't know what to do. We don't know how the optimal option looks like. Okay? So this is what we know and don't know about optimal options for quality distributions. Now let's go back to what we want to show. So again, we're thinking about F, it's a regular distribution, and we want to show that this is the decreasing optimal partition. Now for Q, for the part Q, the conditional distribution is single crossing. So we know exactly how the mechanism is going to look like. So essentially we're going to start at this price here, and here we do the second price, and here we sell this price. Everything is very well defined. But the conditional distribution here is not necessarily single crossing. So we have no idea how the optimal option look like. Maybe we need to apply some ironing, we don't know. Nevertheless, because what we're interested in is the interaction between the two parts and the revenue we can collect, we are still able to show that this is the optimal partition, even though we don't know exactly how the mechanism look like here. Okay, once we go to here, we do know exactly how the mechanism look like. Any questions? Okay. Okay, so this is...
Because you're still getting independence in the
yeah.
bin, whatever, I don't know what color it's.
Yeah, but that's just...
In Q you get independence.
Yes.
And
Yes.
so you know how to solve it.
Yes. Yes.
Whereas there you don't.
But yeah, but the complicated part is getting from here to here.
Yeah, I know.
Challenging part. But yes, at the end we have independence and we know exactly how the mechanisms look like. Yes. Okay. Last families of partitions that we want to talk about. Optimal adjacent partition. Again, now we have the kissing line. Partition the square into 2. XY is in Q if Y is less than TX. And the economic interpretation here is that we collect information about the bidders. The value of bidder X is greater than the value of Y. And this helps us to break symmetry between the bidders. You can see how much we can gain from breaking the symmetry. And what we ask is, what is the revenue maximizing kissing partition? Anyone wants to guess?
If there is a unique solution of this symmetric line, if there are more, then there are any.
Okay. So it's, at least what we're going to prove, it's almost a symmetric line. For the uniform distribution, it is going to be the symmetric line. And in general, if F is a strongly MHR distribution, essentially think about MHR. So don't worry about the strongly. Monotone hazard rate. Yeah, monotone hazard rate. Yeah, subset of regular. Then there exists an optimal partition that is defined by this line. So for x less than tau, we have a constant, and then we have just tx equals x. You want to guess if it's better or worse than the symmetric and the kissing?
No good.
So this is worse. Then breaking the symmetry between the bidders is not as useful as the other thing you've seen. So for the uniform distribution, tx equal x is optimal, but it's only going to collect a revenue of 4/9. So let's see a recap.
So there is no tau, the tau is 0.
Yes, tau is 0 for the uniform distribution. Yeah. Okay, so let's do a recap of what we know. First, for the for intrinsic partitions, so this is for the uniform. The partition is tx equal x, and the allocation that we implement here is not the efficient allocation, right? So in this part, we sell to bidder x even though the value of bidder y is greater. Right? And from this, we can collect a revenue of 12/27. Then we have the decreasing partition that we ask an independent question. So essentially, it's a question that we can someone can ask each bidder separately about this value and then aggregate the two values. And here we collect the revenue slightly larger of 13/27. And for the uniform, the optimal partition based on the three is the symmetric partition where we implement the efficient allocation. In fact, this the fact that the symmetric partition is better does not only hold for the uniform distribution, but it holds in general. So in general, from these three natural families, the optimal thing to do is to ask about the competitiveness of the market. Now, I'm not going to have time to show the whole proof, but let me just tell you a little bit about how we prove that symmetric is better than increasing, because it's the acute argument. Okay, so we have F. It's a strongly MHR distribution, and we want to show that the optimal increasing symmetric partition generates at least as much revenue as the optimal increasing partition. So So what we do is think about something we call the dual partition. What do I mean by this? So we start from the optimal increasing partition. It looks like this. And then what we're going to do is reverse the roles of these partition lines, of these price lines, and the partition line. So instead of this, we're going to think about this partition, which is symmetric. Okay, so these lines are the lines that were previously the price lines, and now here we're going to start in the second price, which is just the same as the partition line here. Now, how much revenue this partition is going to collect? So in this part, we're going to
So
just
that X and Y interchange.
X1 interchange here, exactly.
Yeah, exactly.
Exactly. Yes. So in the blue part, we collect just the same revenue, and in the purple part, we interchange between Y and X, and this is only for the good, right? So if you look at this point, here we start with the X player at some price less than X. Now we're going to start with the Y player at exactly X. So the revenue increased. So this means that for this optimal increasing partition, there's a better symmetric partition. The optimal symmetric partition is even better than that.
What did you use the MHR?
What?
What did you use the strong MHR?
For this, because this is the optimal increasing partition. Okay. Let me summarize. We discussed optimal ways to partition the market. We focused on three natural families of partitions. We talked about increasing, decreasing, symmetric, and we've seen that symmetric is better than both decreasing and increasing. I think this line of work opens the way to many interesting questions. Let me just mention a few. So first, the natural question of what is the optimal partition if we can look at any partition. So here we restricted ourselves just to three specific families. So we know symmetric partition is increasing and decreasing, but I didn't talk about here, but we also have a slightly different model and it's better than all multi-location rules. But what is the globally optimal partition? And this is a pretty challenging question because the partitions doesn't have to be contiguous. So we need to also handle non-contiguous partitions, and the price might not even be monotone. This is one kind of question. We can also think about optimal partitions for other natural families. So one such family is independent partitions. So the bit is composed of clays that can be answered by each player separately. We've seen that such a partition is the optimal decreasing partition. But in general, partitions like this don't have to be contiguous. So it's also a question in this family. What is the optimal partition? Finally,
Again, in each, you preserve independence in each cell. If you ask questions on X and Y separately.
yes.
Because X and Y were independent, so in each cell you preserve independence, which means that should be easy to analyze. Relatively easy.
Sounds like it, but because it can be non-contiguous, it still makes it pretty complicated. So if you ask questions about whether you're between 0.2 and 0.4 or 0.6 and 0.8, this is one partition and the rest is another
I
partition.
know. Start with one bit like you did before. One bit.
No, it's still one bit.
Still one bit. Okay, so one bit and say how many intervals. Question is, can you do better than 1/2? Depending for the uniform again.
Just for reference, with forward information, what is your revenue?
For the uniform, 5 over 12. Sorry, third. Yes.
No?
1/3. We have to allocate the items, so it's 1/3.
No, full
Oh.
information.
Oh, full information.
Slash.
Yeah, 2/3. Last kind of questions could be interesting, something like a bulk number type of questions. So, what do we prefer to do? Recruit another bidder to the market, or get an additional bit of information? What is more useful for the day? So that's it. Thank you. Oh, sorry.
It's just a natural question. What if you have more than one bit of information? You can.
That's
No,
No,
that's
that's not the
should you
last one.
should you get an additional bit of information? I mean,
No,
okay,
that's
compared with
no, that's a different
that's
question.
a question here. Yeah,
So
that's
I'm
a
just saying, what if you can get 2 bits of information?
then you, with 2 bits information, you have like what you can control. Yes, that's a good question. It's already, like just with 1 bit, it's quite complicated. So with 2 bits,
Clearly it's monotonic because any bit you can ignore.
yes,
So 1
yes,
bit,
of course.
yes, and in the end you get
Yeah,
more
in the end,
information.
it's
So no, so in the end, so clearly you're getting more bit. The question is what's how
What's
much
the margin
increment
of-
is worse.
Yeah, and also if it's kind of recursive or a total new problem, I guess it's the latter. But okay.
But if you have 20 bits of information, you can always get 2/3, because you just split it into intervals and get the actual value. Like if you have enough,
it
if you have
goes
epsilon,
to-
1/epsilon, you can
yes.
get 2/3 minus
How
epsilon,
many bits?
something like that.
Yes.
How many bits do you need to get
Yeah.
1 minus epsilon of 4?
Yeah, yeah, that's a very interesting question. Like,
Can it be
You know that
optimal
you know
to
within,
send
composition.
Jakob, can you speak louder?
can it be optimal that the partitions will not be deterministic, namely just a binary signal about the state with the probabilities, namely, with some in each realized state, maybe with some probability I will tell you this answer or the other. Is it obvious that in those settings it's better to have?
You can't get anything from randomization here.
You
So
cannot.
You cannot. More questions, or you want to go to the next talk?
We can go to the next after. Thank you.
You're the next one. Gonna sit this one.
Okay, so when they set up, I'll introduce the next speaker is Alon Eden, and we're very thankful to Alon, who replaced the original speaker on very short notice. And in a minute, I'll know what he's going to talk about. And we gave him more than 3 hours to prepare.
So I guess I should be just going somewhere. And Sigal. Down. Ah, okay. Share. Down. Okay. So.
So in a minute, you'll see what he's going to talk about.
You see it? Don't worry, I won't take away your break. Okay. Thanks, organizers, for having me. Okay, so this talk is kind of apparently it's not intentional, but it will be kind of an interpolation between the last talk where we talked about how predictions can help us, and next talk we'll talk about fairness. So it's a joint work with Ilan, who is here, and Talia and Alsen, who is now Simon, no longer in MIT. Okay, so grandma died, and we want to split inheritance between Alice and Bob, and she left this nice piece of jewelry, this engine vase, and her nice chopper. So the first question is what's fair? How to split fairly, and this talk we're going to talk about a relaxation of proportionality, where an agent deems the allocation fair if they get, let's say if we have 2 players, get half of the value for the entire bundle. And if the item is divisible, we know how to do it, right? We can do the cut and choose procedure and break Bregman's nice vase, but we don't want to do it. So we need a different notion, which we actually talked about today, but I'll redefine it. And the second question is which mechanism should we use? For instance, we can implement round robin. We talked about it today already. So for instance, each one of them can give their preference to the mechanism. So Alice, let's say, likes the chopper, and then the Jure, and then the vase.
So it's ordinal only.
It's let's say let's consider
The
this.
data is only ordinal?
No, it could be you have values, but let's say we want to implement round robin, so they report their valuation and we look at the preference order, let's say. But this is not truthful. Let's say Alice starts and we do round robin, so it takes in terms according to the preference order. Do you see any deviation here? If Alice starts? Okay, so Alice knows that Bob doesn't like the chopper, so she'll say she likes the jewel better than chopper to get her second most preferred item first, and then Bob will take the vase, and she's left with the best item. So this is not truthful. So another question is, which mechanism have nice incentive for this area? Okay, so we'll focus about, most of the talk we'll talk about very simple setting. We have two additive agents. Additive meaning that the value for the vase and the chopper is the value for the vase plus the value for the chopper. And M items. And we look and we define the next the max min share, which is a generalization of proportionality. And unfortunately, now I'm talking about it, we have strong impossibilities even for two players. And in this talk, we will overcome these impossibilities with prediction. We'll show how to overcome these impossibilities if we have some extra information. Okay, so what is the maximum share? Yes?
Is it a problem of computational complexity or missing information that you somehow walk around?
So we'll define well exactly. It's not computational. The problem here is incentives. Incentives will bind you to lose something in the approximation. To lose something. And we'll assume we have extra information to bypass these impossibilities. Okay? So what is the maximum share? So let's say you have two players. And these are the values of, this is the vector one player. So they like this nice iced coffee for €5 and this all these nice so these are the values for the nice quick delicatesse. So the maximum share is the value of 1 if player 1 is a generalization of cut and choose for indivisible items. So let's assume player 1 cuts the items into two bundles, splits them into, partitions them into two bundles, and then player 2, adversary chooses the bundle that player 1 has a higher value for. So in this case, let's compute. This is 8, this is 7. So if player 1 split it this way, player 2 will take the one that player 1 values at 8. And maximum share is the best value it can guarantee, the player can guarantee himself in the worst case. So it's the partition that maximizes the minimum. Is this clear? So in this case, this is the most balanced partition. You want the most balanced partition. And you can generalize it for n players. So first the maximum share of a player is the partition that maximizes the value they can get if they partition the items into n bundles. And then n minus 1 plus get the bundles that worth the most. Okay? So let's practice this. Let's see if you got the definition. I'll give you some vectors of, so this definition only depends on the value of the player, not on the value of the other player. I'll give you some vectors and you tell me what's the maximum share. So what about this partition? What's the maximum share?
127.
Almost. Okay, why is that? What is the partition?
128.
Okay.
120.
So it's
Okay,
2,
so
n equals 2 now.
Huh?
N equals
Yeah,
2.
for n equals to that.
Oh, okay.
We most of the talk there's an epsilon on the end. It's not. Okay, so here split into these items and this item, and it's 127 because we take the minimum. Okay, how about this one? This is pretty simple. 1, okay. This is an important instance, by the way. I'm not just showing it. It's very simple. What about this one?
6.
Okay, 6. And if we change the 5 to infinity,
7.
so 7, yes. So we all know what maximum share is. So some bad news. we would like to have an allocation that always achieves the maximum share for all players. It's possible for 2 players. For more than 2 players, we cannot get perfect maximum share allocation. For 2 players, we can implement the cut and choose. For more than 2 players, it might not be feasible for each player to get a maximum share. So what we look at it instead is approximation. So we want every agent to get at least some alpha fraction or 1 over alpha fraction over the maximum share value. Okay, and Feiger, Sapir, and Tauber showed that it's not possible to get alpha better than closer to 1 than 40 over 39, even for 3 players. And there are some works that show that approximation is possible, with the best result is for a Carmen guard of something just better than I think 4 or 3. Just low. Okay. But you don't want only good.
So that means you get 3/4, right?
3/4 plus
3/4 of that.
Yeah,
Why don't you?
yeah.
I mean, come on. There is a limit to inverting numbers. And when you,
You get at
just
least
say
3/4
which fraction of what you should get you are getting, well, answer is 3/4. What does 4 over 3 tell me? Sorry.
I must say that in my 20-year experience doing conferences, it always comes to the point where someone presents a result of beyond 1 and Sergio complains about why
Yeah.
it's not.
But I think here it's, look, sometimes you may have a point, but here it's really strikingly wrong to say 4.
He said it last time too.
Okay, yeah, I remember the last time.
Well, it's under bad news. You see, the title is bad news. So,
Okay, so in
Sorry,
order to
sorry.
get approximation for any number of players, some of the algorithms are simpler. This is a pretty complicated argument, and it's open. Yeah. Okay. Any more complaints about the notations? Okay. So we don't want only approximation. We also want truthfulness. We want the agent to be incentivized to give us the true data information. And we say an allocation function is truthful if an agent always maximizes the value for the allocation, if they be the true value instead of some vi prime for every vi prime. Okay, this is standard. This is dominant strategy truthfulness. And we have even more bad news if we want this one. So we have this striking result by Amantidis et al. It shows that you cannot get an approximation better than m over 2 when m is the number of items, even for 2 players. No truthful mechanism gets an approximation better than this for the maximum share.
so without truthful, it's okay. Cut and choose.
Yeah, you get
works.
perfect. Yeah,
So
yeah.
adding truthful, that
Yeah,
that's a factor
breaks
of
everything.
n.
But there are some pitfalls. You need it's only for deterministic mechanisms and only for partition mechanisms. But otherwise, this is a very strong negative result. Okay. So and
So
for
randomized, you can get
You can get half an
alpha
SX.
equals 1 or what?
You can get half an SX exposed with truthfulness ex ante, but not known if there's better.
with randomization, there's no better result. No. For special cases, there are maybe, but not for the general case. And it follows from a very complicated characterization showing that basically what you can implement is one agent picks one item. Each agent can pick at most one item. And the rest is kind of predetermined. Okay, so we're going to want to bypass it and want to assume we have some more information. And we use the Lennon-Augmented framework, where we assume that along with the input we have some prediction. The prediction doesn't depend on what the players give us, it's an independent prediction on the input. And we want some nice properties. The first one is consistency, meaning that if we have an accurate prediction, then we get a truth mechanism with better approximation guarantee. But we also want robustness, meaning that if we have a terrible prediction, we still want the same worst case than we had before. Okay? And what would be really nice to get is something in between. So maybe the prediction is not perfect, but maybe it's not way off. Maybe we have some idea of what are the most desirable items, and then we want something in between. We want some performance depending on the noise level. And formally, a A mechanism is
So
alpha.
what's a sorry, I still don't understand. What's a prediction? It's an object. What is it?
It's like in this, the previous talk where we have
A partition of what?
a prediction is just another like side information that you can get without asking the agents. Like in the previous talk, this 1 bit, it was a prediction. This
The goldfish.
the goldfish.
Something about the VIs.
Yeah, something about the VIs. We'll be more specific. Think about, maybe I predict what's your preference order. Maybe I'm wrong, maybe I'm right, maybe I'm somewhere in between. Maybe I know that you like the chopper more than the vase. I predict it, maybe I'm wrong, but maybe it's not that bad.
Well, in the previous talk that was precise. There was no.
Yeah. So here we are.
That's why I'm asking. You say it's like in the previous talk, but it's not. Like
Okay,
in the previous talk.
so consistency is like the previous talk where you have perfect information. Robustness means that maybe the information is totally wrong, and then you have some fallback guarantees. And noisy predictions, we'll talk about what happens if you somewhere in the middle. Okay?
Okay. So previous talk was like your first line.
Yeah.
Okay.
Was on
Now I
consistent.
understood.
Okay.
Okay.
Any more questions? Maybe we'll formally define. So our mechanism is alpha consistent for alpha larger than 1. If when the prediction is fully accurate, like the last talk, we get alpha approximation to the MMS for every player. Okay? A mechanism is beta robust, for beta is typically larger than 1. If the prediction is inaccurate, we still get a beta approximation to the maximum share. Yes, question?
Isn't it always going to be greater than 1? Because alpha is greater than 1?
Yeah, beta is always going to be larger than alpha, because you can always, you can always ignore the prediction, do what's right.
That's the alpha from the no prediction, you mean. Not the alpha from the previous line.
Yes.
That alpha there is not the same as the alpha.
No, this is the alpha like here.
Alpha's
Yeah, typically like it's weird that like if you can get robustness as good as or better than consistency, you don't need the prediction. Right? If you can get something better without the prediction,
but that's because
just
there is a prediction. No, sorry. There is an alpha 0, let's call it, sorry, that is with no prediction.
Okay.
Then there is an alpha with accurate prediction.
Yes.
Then there is a beta with inaccurate prediction.
Yeah.
And the relationship between beta and alpha 0, not beta and alpha.
No, beta and alpha.
No, but what Sergio is saying that you can always revert to the no information and get robustness at least as well.
Yeah. That's awesome.
No, but maybe if you take into account the information because you're hoping for
If you
alpha.
don't care
yeah.
about consistency.
Yeah. You want
consistency.
you want the same mechanism. Just to be clear, you want the same mechanism to be consistent and robust. You don't want to run two mechanisms. You want one mechanism to choose best of both worlds. Okay.
Yeah, therefore beta is always larger than alpha 0. Larger or equal to alpha 0.
Okay. So this framework was started in the online algorithm literature. I see these are all slides, so this is that. Never mind. Okay, and we have improved. It was also used to improve the running time of algorithms to achieve better than the best known bounds. Okay, and recently it was used in mechanism design to bypass impossibilities that are due to incentive constraints. And we'll do something similar to that. Okay. So, which prediction should we use? So we want prediction to make sense. For instance, predicting the exact valuation might be too demanding. We might be off, right? It's not clear that it's kind of weird to assume that we know the entire valuation vector. So instead we study two types of prediction. The first are preference orders or items, so we have full preference list of the agents. So we know, for instance, we don't know the value of the chopper or the vase, but you know that typically Alice would like the chopper over the vase. And we also quantify the accuracy of the prediction by the Kendall tau distance, or the Bubble number, because we also want to have good performance when you have noisy prediction. So this Kendall tau distance is the number of pairs that are flipped in the real prediction, in the real valuation, and in the prediction. So, for instance, we have this ordering of the the items in the prediction, and you have different ordering in the real valuation, so we count the number of pairs that are flipped, that we predicted wrong.
So you have general valuations now or additive?
So this is all for additive.
But then all.
What?
Okay.
So it means that if you're completely wrong about the values, but you got the order right, this is zero difference.
Yeah, exactly. And if you got everything backward, this is basically every pair is flipped. So it's between 0 and m of n plus 1. Question about this and how we quantify the noise.
What you mean? It's a worst case.
Yes.
If there is one very valuable item, you don't care about anything else, and then that makes no sense. But in the worst case, you
No,
don't
but
care about
we'll get
tiny differences, and then that's going to be.
if we're off by the one valuable item, it's okay. We still get a constant approximation. We also study, in addition to this ordering prediction, we also study small space predictions, because these are kind of intuitively, like the one bit, intuitively it's easier to learn this, to invest knowledge in learning these small predictions. So what are our results? So for ordering predictions in two pairs, we have a mechanism that achieves a two consistency, means that when the prediction is right, you get two approximations to maximum share. And a robustness, which is m over 2 rounded up, which is almost matching the lower bound, except the rounding. We can get something better than 2 in consistency, but then we lose in robustness. And actually, it's not a previous result showed that if we get only ordinal information, we cannot get an approximation better than 5 over 4 to the.
Sorry, what are the three rows? I don't understand.
So this is the setting. We look at ordering prediction and two pairs.
So why are the three rows?
Yeah, this is one mechanism that gets two consistency and m over 2 robustness.
Oh, I see.
Yeah.
There's nothing to
It's
do
a trade-off
with
between two numbers.
Yeah.
Okay.
This
You're
is
giving us
another
the-
mechanism that breaks the
You're
two.
giving us the Pareto surface. in
Yeah,
that
yeah.
sense.
In a
Okay.
sense.
It's 3 points on the Pareto surface.
Yeah.
Okay. So-
There will be more points. It's,
yeah, no.
good.
Okay.
And no matter if you get only ordinal information, you cannot break 5 over 4, even if you get it right. This is just an algorithmic lower bound.
So if you draw this,
Okay. For arbitrary prediction, so if we have two pairs, we know that no matter which consistency we have, we cannot do better than m over 2 robustness. This is the low bound of Amanatidis. For trustful mechanisms, we cannot get better than m over 2 if we don't have prediction, basically. And we show that if we want any bounded robustness for any prediction, even if you get the full variation, you cannot get better than 6 over 5 consistency. Moreover, we study, questions? Okay. We also study small space predictions, and we show that basically with logarithmic space in the number of items, can get constant consistency and O of m robustness. For consistency and m minus 1 robustness. And if you allow a little bit more space, log m over epsilon, you get basically the best bounds we get. 2 plus epsilon and m over 2. We also have results for more than.
So it's interesting, whenever you have two numbers, the product is constant. Look if you notice. 2 times m over 2 is the same as 3 over 2 times 2 m over 3. 4 times m is like 2 times m.
Yeah.
I just noticed it. You know?
Okay, interesting. So you have a conjecture.
You're on the Nash curve, you know.
Okay.
The Nash curve with the product is constant.
We didn't show this. This would be very interesting to show the Pareto frontier exactly, but we didn't show that. Yeah, I leave it for further research, for such
It's the statistics of 2.
Okay, for a general n number of players, for a general n number of players, we have a still consistency of 2, we have a mechanism, but we have relaxed guarantees for robustness, which are basically robustness for more than, for MS with more than n players. So we compete against the MS with 3n over 2 players. Like we compete against a relaxed notion of the maximum share. For those of you know, this is similar to the one out of the literature. Okay, so these are results. Okay, and this mechanism and the first two basically if we have a kind of distance of d, which means that we have d pairs that are flipped in the prediction in the actual valuation, we get something like order d, square root d approximation. And this mechanism is oblivious to d. So we just run the very simple mechanism, it doesn't need to know d, and we still get O over square root d. And this interpolates between, so if d is 0, this gives us a constant. If d is m choose 2, this gives us something like order m. So this interpolates nicely between the two extremes. Okay. So let me show you the hammer that we use in order to get master results. So we have some framework which we use. So this the mechanism always gets a prediction as input, the reports of the agents, and some allocation procedure. So these are always the same. So this is always the same, and what we can play with is the prediction we get, the type of prediction, and the type of allocation procedure we get. So this is the input for the framework. Imagine that the prediction is the ordering over items. We predict how the agents order the items, and imagine maybe A is a round robin procedure. So the first step, we'll take the prediction and run the allocation mechanism on the procedure on the prediction, and then we get an initial allocation where Alice gets A1 and Bob gets A2. Notice that this is done without using the report still. Now we do something counterintuitive. We take each agent's favorite item according to prediction, the item we predict the value the most, and give it to the other agent. So we take L2, which is Bob's favorite item, according to prediction, give it to Alice. And vice versa. Why do we do this? Any idea? Why do we just give away the favorite item of an agent to the other agent?
Sounds like a mixing tree strategy.
A what?
Like a mixed tree strategy where you just take the first item, then split on that branch, and then you take it.
I'm not sure if it's related, but okay. So if the predictions are correct, we don't need the reports, right? We can get consistency. We just use the allocation. If it's a good allocation, gets a good approximation, or does a cut and choose, gets perfect consistency. But we also need to account for the case that the prediction is wrong. So the agents need to use the report somehow. So they need to choose in a sense. And what we want them to choose back, to get back, after we plant, is their favorite item. So after we plant the favorite item in the allocation of the other agents, we let them choose according to the reports to steal back an item. So we plant the favorite item according to prediction in the button of the other player, and then they get to choose back, to steal back one item from the allocation of the other player. Why is this truthful?
So can you explain again what are A1 and L2?
Okay, L1 is the favorite item Alice got according to prediction.
So it's a top on the list because you have only the order.
Due to the prediction.
Yeah, it top on this in A1. In A1. You might have a better according to prediction.
Yeah, it's a top in A1.
Yeah.
The prediction is an order on the items for each item. Can be different orders.
For now, assume it's an order. It doesn't have to be.
No, two orders. One
Yeah,
order for
yeah,
Alice, one order for
exactly.
Bob.
Exactly.
That's a prediction.
Okay.
So we just give away the favorite item according to prediction to the outplayer, and then they steal back this item.
So L1 is the best for Alice in A1, and L2 is the best
Yeah.
for Bob in A2.
Exactly.
And I was wondering why don't you call them A and B, just the notation, rather than A1 and A2. It's confusing.
Okay. Send me the list after. Okay.
How can you run the allocation if you only have prediction? Maybe it's not
No.
it's a cardinal, not cardinal information, you only have order.
Yeah, so for round robin, for instance, it depends on the prediction, what prediction you have. But for instance, in order to round a round robin allocation, you only need the ordinal information.
So here, this framework only works if the prediction allows you to run the algorithm with no.
Yeah.
Even though the
This
prediction
A needs to take P as input. Yeah.
It's an allocation procedure given predictions
Yeah.
only.
Yeah.
It's not given anything else.
Okay. So ideally, you want AP to return a good allocation, like that gives approximation maximum share, and yeah. And okay, so why is this truthful? Yes.
T1 and T2 don't depend at all on the reports, and
Okay.
so the best thing they can do is to just take
Yeah.
this item.
So we use the reports only to take back the favorite item, and and T1 and T2 are determined without. Sorry.
So this is because also they are additive, they are not
Yeah, yeah.
it's not true.
Yeah, exactly. This works only. This is in the. Yeah. So yeah. So they get to choose once to take from a bundle that doesn't depend on the reports an item. So they might as well take the favorite item. So this is obviously truthful.
But even if it's not additive, you have a domain.
No, if it depends on what the other one sees.
So it makes from you.
I see.
Yeah.
Sorry, I'm looking for, what's T1 and T2? Something like
Okay.
A1.
It's a temporal.
Yeah.
You call that T1, it's what you get just from that signal.
Yeah.
Okay.
From this.
Okay,
Okay.
sorry, I thought something else is going on.
Okay.
No, okay.
Any more questions? I probably won't get much. So. Okay.
No, okay.
So okay. Good.
So,
Yes.
when you say the mechanism is truthful, completely truthful, or just in regards to the best? Like,
No, completely. You only get to choose. You get T2 and T1 are determined without looking at the reports, only by the predictions. And then you have a set of items. Which one do you want to take back? You take the favorite item. Any more questions about this framework? I'll talk about how to use it to get approximation soon.
Now, the agents know the prediction
Yeah.
before they send
Doesn't
the
matter.
reports.
Doesn't matter. Yes, because it's really because
It's dependent.
it's trivially truthful.
No, but then the report should only care, then you only care about the best item in T2 and in T1, each one, and
Yeah.
all the rest, you don't care to send the true report.
Yeah, but it's you
So-
might as well send your true report because
Well,
you won't gain from debating.
Yeah, but it's, okay.
Yeah.
Yeah, you need to send much less. You only need to send the best.
Yeah.
item.
You only need one item to be right.
Yeah.
Okay, no,
It's
just to
a
see
kind
that-
of
okay, I want to see that I'm following.
No, that's fine. That's good. Somebody. Okay. Okay. So robustness doesn't also depend on it kind of depends on the allocation procedure, but doesn't really depend much. Okay. So the first claim I'm going to claim is each one of the agents gets one of the first top two items. Why is that true? Well, why
It's
is-
always the first unless the other one steals.
Okay,
it.
so
Unless the
let's
prediction is wrong.
so either they have the favorite two items here, and then they lose one item, or one of the best two items is here, and then they will go and steal it back. So it's clear that each agent gets one of the top two items. Okay. And using this, we know that if an agent gets k items, they get an m over an m minus k approximation to their maximum share, or 1 over m minus k fraction of their maximum share. Why is this true? So I'm going to demonstrate it to you. So let's look at so agent I get some allocation xi. We know they get, let's say, the worst case thing that can happen. They get the second highest item, because they get either the highest or the second highest. Let's normalize to 1. What's the worst thing that can happen? The rest of the items for this agent are worth 0. The rest of the items, except the highest one for agent I, are worth 1 for the other agent.
The highest they can be, so that.
And, yeah, exactly. So what's the highest number we can put here?
Okay.
So infinity, oh, it's enough to put m minus k.
Because
To
it
get-
doesn't- she
yeah,
doesn't get it.
yeah. And if you put here m minus k, it's clear that the maximum share of the agent is m minus k, and then you only get 1. So this is the worst case thing that can happen. You can formalize it, not too hard, but this is the intuition, or almost proof, for why is it m minus k. And okay, if this is the case, which type of allocation will give us good robustness guarantees? No? So we want balanced allocation. If we have balanced allocations, this is m over 2, and then each one gets m over 2 robustness. So we want procedures that are balanced. That give us allocation precision A that give us a balanced allocation, such as round robin, for instance. Okay, so I'm going to prove this one. And not surprisingly, we use a round robin allocation. Okay. So Alice gets the third. So we use it for the prediction. Those are gray agents, right? So Alice gets the best item according to prediction. Bob gets the first best item, and so on. I want to claim this gives you a two approximation maximum share when you have two agents. This is not very. This is very simple to see, but I'm going to prove it anyway. Okay. First observation is the value of an agent to the entire bundle of items is at least twice the MMS. Why is that? Because an MMS is a value is a prohibition and you get the worst value of the bundles. So the other one is worth at least that. So we add mu I and something that is larger than mu I, you get 2 mu I fixed. Was this clear, Sergio?
No.
Okay. so why is the value of an agent for all the items, for two agents, is at least twice the maximum share? Because maximum share is defined by some allocation and get the value of the minimum bundle. Okay.
So it's trivial, yeah.
Okay. 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 So is there no trigger? Okay.
No,
Okay.
no, no.
So
After explaining.
no. So I want to say first of all, it's easy to see that according to if the predictions are right, then Alice will get half of her maximum share. Why is that? Because the first item she takes is worth more than the first item, covers for the first item Bob takes. The second item she takes covers for the second item Bob takes. She'll get at least for a value because she chooses first for the entire bundle. So she gets at least a maximum share. It's better than two approximation. For Bob, a simple observation will show that it shows that if you take any item from Bob from the entire bundle, they still get their maximum share value at least for the rest. Because
Proportional up to 1 good.
yeah, because if you lose one item, it's still like the maximum share will put it the maximum share allocation will put it somewhere. Okay. So her value for Bob's value for the entire bundle minus the first item Alice took is worth at least the maximum share, and it shows. Other than that item, we know that the first item it chose covers for the second item. Alice chose the second item it chose covers for the third, and so on. So it gets at least half of that. Okay. So we know that if the predictions are correct, that at least the initial allocation is good. And I want to say if the prediction is the real preference order, we still get the same allocation. Why is that?
So if you, for example, randomize who starts, you get 3 quarters.
Yeah.
Because you get either one or half, and if you randomize, that you take the minimum of the two numbers, then you get 3 quarters.
But you want ex post guarantees. You can get like always truthfulness and half in ex ante. But you want ex post guarantee for.
Yeah, because if you choose just random, just give each one random set, then
the
you get
entire
you finish the whole program.
Or give all items, even if you have n players, give each agent the entire bundle with probability 1/n, but you want ex post guarantees. But this is a good observation. So why is this true? Why, if you predict correctly, the plant still will give them this initial allocation? Exactly. So they still back to you planted the favorite item in the bundle, and they're going to steal it back. If you predicted the preferences correctly. Okay? So this will give us to consistency. Okay. And round robin allocations are balanced, so we saw already that
So what you're saying, alpha equals alpha 0, is that correct, or I'm misunderstanding? In your notation.
Alpha.
What's this two
Alpha greater than equal to 1.
Yeah, alpha.
Greater than 2.
Yeah.
For consistency.
Yeah, alpha.
So it's the same as.
Is that beta robustness on the second?
Yeah. Okay. And the robustness is m/2 because of the balance allocations. Okay. So this is the first result. Pretty simple. How do you break 2? Okay. So what happened here? We had something weird, right? We wanted 2 approximation, but Alice got something too good. Right? She got her maximum share because she was first. So we want to fix that.
So you use something better than EF1, which gives you better in this case, but less balanced allocation.
Yeah. So would you run? So she chooses first. So we need to punish her somehow to balance the cases. How would
So
we
what
do?
we choose twice.
Okay, what? Sorry.
We choose two items.
Yeah. So exactly. Okay. So we change the round robin allocation to be the following. Alex chooses first, takes one item, and then Bob each round takes two items. And you can show this balances everything out, and both of them get 2/3 of the maximum share.
Each round, not only in the first step.
Each round, you need to do it each round.
What if you do A, B, B, A, A, B, B, A?
What?
What if you do the A, B, B, A, B, B, A? Should I go?
It wouldn't work, I think. Because you can, I think it wouldn't work if you have one large item and the rest. If you want them to take more, the second one, it wouldn't work, I think. Okay. But we get something a little bit less balanced, so we get 2m/3. And let me skip, okay.
Can you do it? Can I do better?
Yeah, there's a proof you cannot do better actually. It's from also from Amanatidis that I took other predictions.
So for this, you cannot
do better.
If you want three over two consistency,
Like with other prediction, you cannot do better than this go to pairs.
But by the way, Alon, the one thing I had to do today, which is keep track of your time, I failed to do.
No, I look
so,
at it.
Okay, so you are
Yeah.
responsible for your
Yeah.
It's a truthful mechanism.
No, we will finish on time. We don't have to talk.
Consistent and robust.
Okay, so the same algorithm will work even if you have if your prediction is noisy. If you have bad prediction, and I won't prove it to you, I'm just gonna say we're gonna use the 0-1 principle of Yossi to show that basically you can analyze instances where the values are either 0 or 1. If we get an approximation in each one of these instances, we get approximation for general valuations. And if we have 0-1, so if we have 0-1 instances, and we have a budget of D to move items to make them wrong, we can move it at most square D items in order to reach its budget. Right? We can take the favorite square D items and push them back. This is the best thing we can do, and this will exhaust our budget. We'll use. I won't say anything about it. I should have this one, but okay. I'm going to skip the small space mechanism. Never mind, you can do it. But it's the same framework. You just change the allocation function and the prediction. So what I want to say is that we have this hammer of this framework and we use it. We just change the allocation function and the prediction and get different trade-offs and different results. What we do for antlers is a bit more subtle. We basically we generalize the mechanism. We use a modified round-robin allocation to get an additional allocation, and then we do it recursively. We split the agents into two sets. One set plants the favorite item according to prediction in the other set, and then they steal back the items. I won't go over the details, and then after they do that, you implement it recursively. I think I don't have time because I'm out of time, but basically you can continue with this process recursively, and each time they get a set that doesn't really depend on their report to choose from, and this is truthful. And this is gives us the, I won't go over the details, you can read the paper. Or talk to me afterwards if you want, but we get this. And these are also the future directions. So there are gaps, like is Sergio's conjecture that the product has to be M true? Can you get something better, some better trade-off? What's the lowest consistency you can get with the robustness of M? And can you get something for N players with robustness guarantees that aren't weaker? And I think maybe before we note it, this doesn't work beyond additive, because the item you want to steal back, for instance, you have some model evaluations, depends on the item somebody stole back from you. So can we do something beyond additive? And yeah, okay, so thank you. And